gentlemen. First of all, I would like to say thank you very much for organizing a very interesting garden party yesterday. Thank you. And today we open second day. We have distinguished guest, distinguished professor Witold Pedrycz. Witold Pedrycz, some case, he is from this university. He earned his master degree. I don't know how far, when, but a long time ago. Yes. Yes, okay. In previous century, okay. But more serious. He is IEEE Life Fellow. He is professor in the Department of Electrical and Computer Engineering, University of Alberta in Edmonton, it is Canada. He is also with the System Research Institute of the Polish Academy of Sciences in Warsaw, Poland. And as well, in Academy of Science, he has another membership. He is a member of the Polish Academy of Science and fellow of Royal Society of Canada. Moreover, he is award from the IEEE System Man and Cybernetic Society, IEEE Canada Computer Engineering Medal, Kaiser Prize of Soft Computing from European Center for Soft Computing, as well a Killam Prize, a Fuzzy Pioneer Award from IEEE. It is very important awards and a Computational Intelligence School, and as well in 2019 Medals of Services Award from IEEE System Man and Cybernetic Society. His main research direction involve computational intelligence, gradual computing, machine learning, and many other as well direction and area of research. But in general, it is computer science, I can say technical and theory of computer science. As well, Professor Pedrycz serves as editor-in-chief of Information Sciences Journal, editor-in-chief on wireless data mining and knowledge discovery, is a journal published by Wiley, and as well, he is co-editor-in-chief of International Journal of Granular Computing. I think it is last years, granular computing is very important part of his research, I think. It is Springer, and of course, he is a member as well in a Journal of Data Information and Management, Springer, and as well in this time and this place, I would like to thank Witold that he support as well our Polish journal, International Journal of Applied Mathematics and Computer Science. Thank you for your support, and really your support was very important. But this journal just now has a pretty good position among the international community. Witold, thank you that you accepted our invitation. And just now, please, your time.
Okay, thank you very much. Well, first of all, I'd like to congratulate the organizers for this very important event. It has a very long history. And I'm really very much happy being here because this is my alma mater. Many years ago, last century, I completed my master and PhD degree, and it's definitely always a wonderful opportunity to come here again. So I'd like to thank you very much for the invitation. Let's keep moving with our main theme today. I suppose machine learning has been around at the forefront of many research and application developments. I think the term AI, the term machine learning, is very visible across the research community, but also it is visible across just the public. So the question is, where are we today? What we have accomplished and what are the challenges. Because if we are contemplating future development in this area, we have to become very much alerted and aware to the fact that there are some open issues that are not going to vanish, but they deserve our attention. So having said that, here is a brief agenda, what I would like to cover today. And my talk is going to be a little bit mixture of some conceptual developments, but time to time, I would like to delve into some more technical discussion. I know that anytime formulas appear, no matter what audience you are talking to, the level of interest starts to eventually disappear. So hopefully I'm not going to bore you too much with this. What I said, I'd like to look at machine learning or AI. Honestly speaking, we have to consider that AI today is predominantly machine learning. It's not what we've seen in the 70s or 80s, that there were different trends that came under the rubric of artificial intelligence. And the entire agenda tries to eventually portray the key challenges. So I would like to talk about green machine learning. I would like to talk about credibility of results being produced by machine learning architectures, and talk about ways how we can eventually address these issues. And then I'd like to talk about some illustrative applications in terms of transfer learning and federated learning. They are really coming from this kind of applied side of the entire area. Now, if somebody asks you about machine learning and you would like to give a very brief summary of the area, probably there are just a couple of items that are quite visible. We are dealing with a humongous amount of data. Those are masses of data that we have to process, and essentially they are behind the success of a lot of developments. You have a lot of architectures, you have a lot of learning schemes, and this sort of entire development is progressing very rapidly. Now, what we can also observe is that there are essentially different areas that are targeted by machine learning. And the common denominator is that there are critical areas. So in other words, that such as autonomous vehicle or healthcare, that essentially you have to be aware of the facts, aware of the outcomes of your decisions, or decisions of the system that you design. How credible are the results? Are your results, are your decisions essentially safe, either for the environment or to the user? And I suppose there is really a lot of discussion about this, sometimes going into this kind of folklore about AI taking over humanity. I would prefer not to speculate about this, but there are some sort of points being raised. Now, if you look at challenges or some stumbling blocks, and there are a number of those, that probably some of them could be quite clearly highlighted. Namely, you are doing a lot of computing, there is no free lunch. You have to pay for that in terms of amount of sort of computing of electricity, let's put it this bluntly. There is the question, anytime you build a more complex model and they to be visible in deep learning, then you are losing capability of doing any interpretability and explainability. It does not come as a feature of those models, okay? And along with this, you have a question of credibility. I've mentioned this a bit earlier. How credible are the results? How much confidence do you have in the result being produced by machine learning, let's say, classifier or predictor? There is a question of privacy data. Well, privacy, on the one hand, you have a lot of data. On the other hand, there are some possessive owners of the data. They do not want to share the data for many different reasons. There's also a question that comes with sort of brittleness of machine learning solutions. So the bottom line is we cannot sort of admit, we can admit that these challenges are not going to disappear, they are going to become more visible. So the question is, how are you going to address them? Well, there were a number of different developments. I would like to point at two of them, namely green artificial intelligence and explainable artificial intelligence. That's something that happened just around 5-6 years ago. It was really a very important development because it raised awareness. Well, hey, if you would like to see a continuous progress, then you have to look at this area from a kind of broader perspective. And this somewhat brings us to the situation that we have to get out of this technical content only, so something that we are developing today, and try to embrace a more general perspective that I would call society-oriented design environment of machine learning. Because all this, or most of these issues I raised, they are related with the society. It's not really just a development in a kind of very plain way in the laboratory. You have to know the implications, okay? So from this point of view, green AI and green and explainable AI really offer you a certain broader perspective. But I always believe that you have to look backward. You have to see what has been done so far, what technologies were developed. Maybe they were put on the back burner, but maybe it's a good time to revitalize them. And I would like also to mention some of them. Existing concepts that have been around, but they have to put forward on the main stage and see how it's going to develop. So in this sense, we are seeing that this is this technical content of this entire area, but there are a number of those challenges, and you have to go broader. In particular, you have to look beyond this, essentially, this algorithmic core of machine learning. So again, there are just what you can call society-oriented machine learning. I talk about, I mentioned green machine learning or green AI, and I suppose from this point of view, it becomes very much important that we realize that there is a very humongous challenge today, and it's going to be far, far bigger in the future. Essentially, you look at amount of computing. This is just a quite sort of recent position paper, white paper on green AI. And you look at the data, I'd like to mention that this Y coordinate is in the log scale. So essentially, when you see the development of different architectures that are very well known, we see how much computing has to go into this, or subsequently, what about carbon footprint, okay? So on the one hand, we see a lot of those very positive news, but on the other hand, we have to acknowledge that AI technology or machine learning technology is very much power hungry. What are the implications? What are the numbers behind this? Well, again, we are complaining about carbon footprint of our transportation systems. We are doing a lot of things to rectify the problem, but what about here? And it is obviously straightforward that you have to pay a price if you are developing huge architectures. You are developing networks that are composed of billions of parameters. You have to do the training. You have to realize that this training is going to take time. GPT-4. That's probably an interesting development because everybody talks about chat GPT, but I would like to draw your attention to only one parameter, like looking at the number of parameters and looking at the electricity bill, that it has to come hand in hand with the development of this architecture. For the comparison, you can look about household usage of electricity, so you can compare these two numbers. And this trend is going to expand, is going to become more and more visible. And here are just more numbers. So essentially, we are seeing that over a few years, we are talking about a tremendous growth of energy consumption. This is not going to be sustainable. So the question is, what can we do with this? Green machine learning or green AI, it is really a certain position or it is a certain development, but it's worth stressing that essentially it does not offer any recipe. It really raises awareness about the problem. Well, they have a lot of items on the agenda. I'm trying to pick up one of them. And there is a very important factor and fact that one has to acknowledge. We are doing something that offers a disservice to the entire area. We are really looking at one criterion, one objective function, with the intent of minimizing it. So you can talk about prediction, you are talking about classification rate, you are buying better outcome by bringing more sort of complicated architectures. So essentially, the return on investment is going to be, or it is far, far lower. Well, all of us know what the limits are, because if we admit this kind of Bayesian way of thinking, that we know that there is a limit in terms of the essentially Bayesian error. But this is really only a sort of a minor observation that we can make here. But green AI tries to bring a concept of efficiency at the kind of broader sense. So efficiency could be viewed as a carbon emission, but also amount of time you have to spend on developing the models. But there are a number of other factors that cannot be ignored. So in other words, we are moving from machine learning to what we can call a green machine learning, and essentially we are sort of trying to bring some new technologies, revisit some existing technologies, and create this kind of, I think, more comprehensive, more holistic agenda. Among the technologies that, in my opinion, are promising, one of them is quite visible, namely concepts of granular computing and information granulas. Well, probably some people here must have heard about fuzzy sets, must have heard about probabilities, probably everybody. And the question is, when we are dealing with numbers and we are dealing with solutions, and humans are recipients of these solutions, what is our way of perceiving the world, coping with complexities, organizing our knowledge? Well, surely we are not reasoning, we are not doing numeric processing, but our way of sort of perception of the world happens at the higher level of abstraction. So in other words, naturally, we are building information granulas so that essentially they reflect reality, they allow us to reduce complexity, they allow us to interpret the results, and from this perspective, it offers some interesting and tangible benefits to machine learning today. As I said, when we are talking about information granulas, the concept is intuitively appealing and very simple. But when it comes to processing, you have to bring a formal framework. Oh, sorry, I'm sorry. Sorry. We are talking about essentially concepts such as sets, fuzzy sets, probabilities, rough sets, and so on. There is a lot of contribution in this area. For instance, Professor Kacprzyk really made a tremendous contribution to fuzzy sets. Late Professor Pawlak was the founder of rough sets. Well, if you ask yourself, why are you using sets? Well, because you're starting it from the childhood, okay? But the point is that essentially you are forming a certain abstract description of reality. You are bringing some items that have some sort of similarities, and they come under the same roof of a certain information granular. So that's really where we can see some advantages, and I would like to focus on the two of them with respect to interpretability and explainability, and with respect to essentially confidence and credibility of the results. Another item that is very much high on the agenda of machine learning is related to explainability, explainable machine learning. This becomes very much evident because essentially the complexities of the models are going to be higher, are high now, and essentially people cannot understand how these systems operate. There are just a certain distinction between interpretability and explainability. When we are talking about interpretability, it's really related to the faculty how the results can be easily understood, comprehended by the user. So essentially, if I give you a certain decision, a certain outcome, you should have some semantics clearly defined behind the sort of my sort of description. So the result has to be interpretable. For instance, if you are talking about a numeric value, well, it does not tell you too much. You have to put in a certain context, namely a value of a certain variable that describes what, and essentially you have to define the space. I think if you give the number, somebody tells you its inflation rate is 15%, okay? Well, it says nothing because you have not set up the context. Well, perhaps here is not it's not so good. But if you go to Zimbabwe, everybody will say, well, that's probably essentially not so bad. Is that right? So this is the point how we sort of look at this aspect of interpretability. Explainability is really about the way how you can explain your results. So you have a deep learning architecture that has a lot of layers. You get the result, and you want to get some explanation. Mathematically speaking, it's really about reversibility of this entire model. So if you go from essentially from the output, just looking at the sort of language of automatic control, and you are asking about the input. What is the input that sort of implied this output? Obviously, the question if the entire transformation is reversible, okay? So in other words, the point is that you would like to have this faculty of explainability that is built as a part of machine learning architecture. Well, sometimes it's designed, the system is designed in such a way that this criterion is taken into account. Sometimes this criterion is addressed once the model has been built. It's a kind of post-mortem step, okay? But nevertheless, it becomes very much evident that we should essentially strive for explainabilities. In many cases, we are forced to do that because of some legal requirements. And notice that this is a question, if you have some result that you can explain, then you have higher sort of confidence in action you are taking sort of the next step. So explainable AI happened in, was sort of put forward in 2017. It was just done at DARPA. But honestly speaking, I always love to see what happened before, because what they emphasize is the fact that there are this kind of two conflicting driving forces. We are talking about essentially explainability, and you are talking about sort of learning and performance of the model. And essentially you are seeing that these two criteria are in conflict. So you may have just model that essentially has some explainability, but if you want to increase it, then you are proceeding with the higher then you are paid the price in terms of explainability. But what I think is important is to emphasize that you have to go backward, because they, on the agenda of explainable AI, the point was that, well, there are some architectures that are naturally more explainable. So you contrast neural networks vis-a-vis rule-based models and vis-a-vis, for instance, the simplest possible classifier like nearest neighbor classifier. They think that this is something new. I want you to go back to the 70s, where people were talking in AI were talking about knowledge representation, and they were talking about ideas of essentially rule-based models. So at this time, we had this sort of quest addressed as well. Another challenge, so as I like to make a point, that there is an important to run a research along this line, but we have to remember that there were some developments done in the past. So it's not something that we should reinvent a wheel. Another question that very much is central to the application of machine learning is about credibility of the models or credibility of the results. And I think the idea is very simple. Imagine that you develop your machine learning model on the basis of some data. Those are blue points that are presented here. And now you deploy the model and you get a certain new input. Obviously, the machine learning model is going to return the results on the basis of this very obvious transformation. Namely, you calculate just the input, you have the input and you calculate the output, so you get a certain result. Intuition tells us that it looks okay, but what if you get a new situation that is quite remote from the data that you used to build your machine learning architecture? Something is being shown here, or something that is present here. Well, the model is going to return the result that is a certain numeric value. So as a matter of fact, you cannot distinguish how credible this result is. All of us have this intuitive sense that this has to come with some measure of some figure of merit. Okay? So something that could be not a number, but could be regarded as information granular. Okay? So those are the questions you can ask yourself. How credible is the result? How much confidence could you associate? And what is very much important, can you argue that the system that you design has to come with some self-awareness mechanism? So the system should really produce some warning message to you saying, I cannot reason, or I can give you the result that is not very specific, that is just an information granular, not a single numeric value. Well, in many cases, these machine learning architectures are not developed this way. They are bluntly produce the result, whatever the input is. Now, if I ask the audience here, how could you proceed with this? Knowing what we studied so far, okay? Could we reinvent the wheel? Well, the answer is, well, not necessarily, because our philosophy is that your result should not be numeric, but should be an information granular. Could be an interval, could be a fuzzy set, could be a probability density function. So I can give you the result that is an information granular. And what is interesting, that now you go backward and ask yourself, was that done outside the realm of machine learning on an everyday basis? And the answer is positive, okay? Because what we are really talking about is confidence intervals, prediction intervals. And this is a textbook material from any course in statistical inference. Notice that essentially we are talking about some concept of coverage that is conveyed by the confidence interval or prediction interval. So again, think about information granulas. Those are just interval information granulas. Well, this is just what we know very well in linear regression, okay? It's not, the model itself is numeric, but the result that is conveyed to the user is an information granula, is an interval. So this essentially puts us forward on the path to think about information granularity as a certain concept that is very much linked to the idea, or linked to as a vehicle to quantify the credibility of the result. And we can take another approach. We can think about a granular model. So in other words, we say we developed a machine learning model that is numeric, and we are going to augment this model by its kind of granular counterpart by admitting that essentially the model is not perfect, and we can quantify this phenomenon by bringing another layer that I can refer to as a granular model. And this layer is built by bringing a concept of information granularity into the existing model as being portrayed here. So you can see that the core part is the model you've already designed, and this layer around is just a information granular layer that essentially elevates the numeric model to its granular counterpart by essentially having an additional knob such as level of information granularity. This is just a certain design asset we can think of. And our objective is that this information granular has to satisfy two requirements. One is very similar to what I was talking about a moment ago, namely coverage. You'd like to see that the results becomes covered by this information granular. So again, it sounds very much like confidence interval, prediction interval. But also from the point of view of sort of value of the result, you would like to have a certain specificity of the result. So in other words, that should not be really a very broad interval. You get this coverage criterion satisfied, but specificity, the results that you are getting is sort of not specific enough. So there are just two criteria. If you portray them in the sort of these two coordinates, then they are in conflict. You bring higher coverage, you are paying a price in sort of specificity. So formally speaking, this is just a kind of key idea. You elevate numeric values, numeric parameters of the model into the granular counterpart having this level of information granularity. So for instance, for the interval, it could be a very simple transformation. You take the point and you build an interval, so therefore the result of your model becomes also an interval. And the quality of this result is expressed in terms of coverage and specificity. So those are just a kind of underlying formulas. So the first one, everybody can recognize, is very much within the realm of what we did in probability. A specificity is related to the size of the information granula. For instance, in terms of interval, it's the size of the interval, the length of interval. In terms of fuzzy set, would be just a sort of generalization using so-called alpha cuts. And because these criteria are in conflict, that you want to maximize the product of those two. So coverage and specificity maximum over the level of information granularity. So again, we see that in terms of credibility of the model, the credibility of the results, it's not only a numeric result, but it is an information granular. Okay, now let us move on and look at two very practically relevant scenarios where this information granularity and could be developed, could be applied. The first one is about federated learning. I think the term has been around for a couple of years, and the underlying idea was the following. Essentially, imagine that you have data that are distributed, okay? You have distributed data, they are owned by a number of local owners, and you want, on the basis of this data, to build a holistic model, okay? But there is one clear obstacle. The data cannot be shared. So I think the owners are possessive, there are maybe some legal sort of constraints, or eventually this data cannot be moved to a central place to do a model building. So I think this really creates a certain paradigm shift, because essentially when we are talking about machine learning, our kind of dogma is that you start with data, you build a model. So data is the starting point. Now here you don't have that immediate, you don't have a direct access to data. So the situation looks as portrayed here, that you have some large number of those local owners called clients, so this might be handheld devices, and you have one environment, or you have one entity called server, whose role is to build the model, okay? But the point is that essentially this model, or sort of this server, does not have direct access to data. So essentially, we can envision that the development scenario could look like this. I'm interacting with the clients, I'm providing them with some initial position as to the model, let's say parameters of the model, and then I convey these parameters, the model, to the individual clients. Clients confront this model with their own data. They cannot share the data, so they convey some guidance to the server. They simply say, well, I can tell you about the performance of the model you constructed. So that's what I call here knowledge. So notice that the way of communication is at the higher level of abstraction. There are some pieces of knowledge that seem to be eventually useful in this entire process. So here is just the main idea. And we've seen a lot of applications. I think Internet of Things is one of this kind of very visible flagship areas here. However, from the point of view of computing, well, we have to deal with this problem, because when I use the term knowledge, it's probably overused. It does not have a technical connotation, what this knowledge stands for, okay? So we have to clarify this. And in the literature, we have a lot of developments. There are just two kind of mainstream and a lot of scenarios in between. One is very simple. It's called average federated learning. What this means that essentially the server sends the model to the individual client. Client considers this as a starting point and builds its own local model and sends the parameters of the model to the server. So that's what is being portrayed here. So I think it sends the parameters of this model to the server, and the same happens with other clients. And the server does very simple process. It takes these parameters and does averaging. Maybe there's something more sophisticated than that, but essentially what it does, it really creates a certain aggregation of the parameters, and the process is iterative, so you can have just another step of iteration, and hopefully the method or the approach converges. Well, I'm saying hopefully because notice that from the point of view of machine learning, you cannot guarantee that the data that are present at the position of the individual clients have the same probabilistic characteristics. So I think something that we have to address just later on, and saying what is the credibility of the model you constructed in this way. Another approach that you can find is gradient descent learning. So essentially what the server receives are not the parameters of the model, but they are the gradient of the loss function being computed by the individual client with regard to its own data, okay? There's also a question about the format of the data, the so-called vertical and horizontal. There is a lot of literature on these studies, a lot of developments. I'd like to emphasize that you may have a huge number of clients going into thousands or hundreds of thousands, because you can think about a sensor that sort of generates the data or stores the data and only communicates with the server at the higher level. And there's also a question of communication sort of schemes, because if you have a lot of clients involved in the process, then how are you going to organize the interaction with the server so that you treat all the clients in a fair manner? However, there is one point that has not been sort of addressed in detail, namely, you build the model. How good is this model? Because as I said, the data are not homogeneous, okay? So there's this IID assumption in machine learning may not be valid. Well, the point is that we can augment the model built in this way by forming its granular counterpart. How we can do that? Essentially, you build the model was built by the server sends this model, and the model is confronted with the data at each client. The client then determines this granular model. So essentially, this is the operation that is being presented symbolically in this way. So essentially, for each model, for each client, you have the level of information, optimal level of information granularity that it comes with this model. And then what happens is that these levels of information granularity are sent to the server, and the server aggregates them and obtains the value of this kind of aggregated value that essentially builds up the granular model. So essentially, at the end of the entire process, the model becomes granular, and then you have a certain tangible measure of essentially credibility of the results of this model. So it's not only the model you construct in this federated learning, but you are talking about credibility of this model. And obviously, anytime you see the operation of aggregation, there are a lot of possibilities. So I think there's the question how to choose the aggregation operator. So there's another step here that you can think of, namely you can take a certain family of aggregation operators and you can do the optimization following this particular objective function. So you'd like to see that essentially the aggregation that you realize is such that it maximizes these products of coverage and specificity that you determine for the individual clients. So you can choose a certain aggregation operator, perhaps from a certain family, and here is just one of the possibilities, like generalized average, because that's a pretty I would say, a large family of aggregation operators. So not only that you optimize the parameters of this aggregation operator, but you can also think about this one parameter that just moves you from arithmetic mean that we use on an everyday basis to the maximum, minimum, and so on. And just another topic that is very much, again, linked to green machine learning is comes under the name of transfer learning. Well, if you have the knowledge that you acquired in the form of the model in the past, and you put a humongous investment to build this model, how are you going to proceed if you see new environment? Are you going to build the model from scratch, or are you going to become smarter and eventually reuse the knowledge that you acquired? So reuse the model. And that's really just the key idea. It is not a new one, because it's been around in the domain of AI for a long time, and essentially it came under, that's not me, it comes under different names, such as, for instance, learning by analogy, domain adaptation, pre-training. So the key idea is very simple. You have a so-called source domain, so that's that you use to build your model. So you have a certain, in the source domain, you have a domain and you have a certain task, let's say a classification task. And now you have a new, what's called environment, say target domain, that you have new data, and instead of building the model that essentially from scratch, you are going to essentially use this model in this new environment. Well, it looks encouraging, but there is one interesting point that has to be stressed, because anytime you bring the model from the environment, from one environment to a new environment, how good is your model, okay? If you don't tell me this, then essentially you are really doing a little bit of risky business. So the idea is that we can essentially augment the model when transferring it to this new environment, to the target domain, by essentially forming its sort of granular generalization. So any information in the result of this model in the target domain are going to produce information granulas. Well, this is referred to as a passive approach, because you are really doing nothing. You take the model, you construct it, and you bring it to the new environment, and you see, well, how is the sort of granular footprint of this model. It could be okay, it could be acceptable, but if this target and source domain are more distinct, are moving apart, then essentially this is indicated by the level of information granularity of the results. So you are losing specificity of the results, but at the same time, you have to take some more active position here. And this leads us to this point, this idea of active approach. So active approach is such that you are reusing the model, more specifically, you are reusing this granular counterpart that is being portrayed here, but also you can take maybe some data from the target domain and use them to build the model here. So in other words, the design of the model that you are going to form is based on this data from the target domain, maybe a subset, so then saying it's kind of savings that you can have, and also getting some guidance coming from the granular model. So this is the part that are being shown here. So altogether, they are just these two components that form an objective function. One point that has to be stressed that essentially, when you are talking about a target domain, this is just a classic objective function that is based on the sort of numeric discussion, and another one is a granular one. So from this perspective, you can translate the entire problem. I'm not going into details, I'm trying to highlight the idea of the constructed loss function that involves two components. One is coming from the data. This is what you want to minimize on the basis of data from the target domain, but this one is essentially a kind of guidance force. What we can know in machine learning is a sort of regularization term, and because they are here, you have information granulars, we can refer to this as a granular regularization. So this is the loss function, and then you proceed with the optimization of it using whatever method you have available. Particularly, you can proceed with some gradient-based methods. There could be another alternative that you may have different source domains, and the models you build on them could be brought together into the development of a model in the target domain. So again, here, the scenario is very much similar to the previous one, with the only exception that we have just a number of these granular navigation hints that have to be taken into the loss function, which now looks a little bit more complicated because we are trying to take into account a number of these granular navigation hints. And again, the optimization problem is done in the same way as before. So in summary, in this sort of idea or in this environment of transfer learning, we are seeing that granularity of the model and the granular hints offer you a certain sound sort of navigation, a sound component in the entire design process. I suppose my time is up, so here just kind of a few concluding comments. Namely, my intent was to offer some perspective at machine learning today. Obviously, it's very subjective. You may disagree with me, and that's perfectly fine. But I'd like to sort of indicate that we are seeing a very rapid, very omnipresent development of machine learning technology, but we have to become aware that there are some challenges that have to be addressed. And how to do that? Well, first of all, we have to admit that there is some tendencies, there are some kind of positions that people take in terms of the holistic development of the architectures. But also what is important is that we have to think about looking at the past, where some of the developments, some of the constructs could be revisited. So with this, I would like to express my thanks, and if you have any questions, I will be happy to answer them and engage in any discussion. Thank you very much.
Thank you a lot for very interesting talk, very hot talk, presentation. And I think we have time for a few questions, comments. Machine learning and another topics was very interesting. Yes, please.
I have 15 minutes for questions and answers.
Yes, we have 10 minutes.
Yeah.
Thank you for a very interesting talk. I have a question regarding the concept of granular modeling of information. Because especially when considering that it reduces in a way to interval information, aren't we generally going towards full probability model and getting a probability representation of all variables, in this case, like in Bayesian statistics, when you can get joint distribution of all parameters? Because if you have intervals, you generally go into marginal distributions for all of the parameters with some kind of independence between them. And if you go full probability joint model, then it will probably go this way. And like philosophically speaking, most of those concepts of generalization, like for example fuzzy sets, all at the end of the day show a bit inferior to normal probability representation. When you go to the probability concepts like those given by Cox, you get like this concept like of probability as a logic of science, something like that.
Yeah, I think there's been a lot of discussion about fuzzy sets and probabilities in the past. I probably don't want to venture into this in sort of general terms. I think, first of all, anytime you build an information granular, you have to admit that there is some construction. You have to design information granulars, okay? So it's a question, if you are talking about probability functions or probability density functions, then essentially you have to do estimation. So this is the first point. Now, when it comes to fuzzy sets, or let's say information granulars, thank you very much, then we have to admit, then again, it's a different way of looking at the knowledge, because if probabilities are based upon data, fuzzy sets may reflect upon some additional knowledge offered outside the domain of data. So I think I'm not saying there are going to be a kind of conflicting views, but it could be just some supplementary perspective. I was talking about probability. I have not mentioned this, but I think from my perspective, what we are seeing kind of advantage in terms of credibility of models or granular models is, for instance, proceeding with Bayesian regression. Because in Bayesian regression, the result is an information granular that is typically described as some normal distribution. So from this perspective, you can talk about credibility that essentially becomes really quantified, for instance, by the variance of this particular result. That's probably just a kind of key points I'd like to make. maybe. Yes.
You said that the data is sent to clients and clients just evaluate the model. And do you think, you said about this aggregation, that there are different ways of aggregation. And what do you think about evaluating the quality of data of clients? So some clients maybe, we may evaluate that, for instance, data from these clients are not so valuable.
I think typically in the existing approaches, the quality of the client is characterized by the amount of data, which obviously we have to admit has nothing to do with the quality, but essentially if you talk about the number of data being sent by the, not data being sent, but number of data being sort of generated by the client, then you have some modified coefficients in the formulas for gradient-based, for gradient or for average learning. Now, the quality of the data would be more difficult to assess because essentially if I don't have access to data as the server, then I cannot give you a kind of immediate figure of merit. But that's something what essentially becomes very much evident if you are talking about some malicious clients who are going to essentially poison the development of the model. So again, there are just a number of approaches that people try to accommodate here. But well, we have to admit that the clients may have different perspective at the problem. So I think they are not wrong, but they have different, they have their own points of view. If you are going to bring them together, that is going to have a certain impact that is of a negative nature, okay? And also is the problem, anytime you do aggregation or you are trying to build consensus, you're doing some consensus, we have to admit that the majority is going to prevail unless you take some more specialized measures to do that. So I don't think there is a single answer, and I don't think that there is a complete solution to the problem.
Okay, thank you a lot for your comments. And maybe can I ask you, could you explain more this idea on green machine learning? This can be applicable, can be in the future, because really this idea is very, very nice. And
well, I suppose when the paper, this white paper has been published, what's called Green AI, I think the main value of this paper might be that they simply try to raise awareness of the problems. That is, you have to do about, you talk about computing, you have to talk about some other factors. It's not only computing. They have, if you look at the paper, they are talking about a number of other factors which are probably important, but they are not measurable. So in other words, they are talking about fairness. They are talking about essentially a way of how researchers coming from different countries could contribute to the development of sort of machine learning areas. Some of them could be disadvantaged. I decided not to talk about them because it's a question of measuring.
Okay, thank you. I think it is time to say thank you a lot once again, Professor Witold Pedrycz. Thank you.